Hello and welcome to the AIM webinar series. Today's session is Securing the Aerospace and Defense Supply Chains with Non-Clonable Security Markers, and our speaker today is Mark Manning, founder and CEO of iTRACE Technologies. First, a little bit about AIM. AIM is the Industry Association for Automatic Identification and Data Capture Technologies. We are an unbiased resource for advocacy of the effective use of these important technologies, creating a vibrant community for networking, which creates and maintains standards and other educational materials. If you are not an AIM member and are in this space, you really need to be. Reach out to us to learn more on our opportunities to network, solve industry issues, and influence the automatic identification and data capture industry. Now, briefly, I will go over the AIM antitrust policy. It is the policy of AIM to conduct its operations in strict compliance with the antitrust laws. No AIM activity shall create even the appearance of a violation of the letter or spirit of the antitrust laws. And some other housekeeping notes. All participants are muted in this webinar, but we do want your participation. Send our panel questions via the Q&A option that you can find at the bottom of the application screen. Questions will be answered at the end of the webinar, and all registrants to the webinar will receive a notification when the recording is available to view on our YouTube channel. And now I'd like to turn it over to our speaker, Mark. Thanks for joining us today.
Thank you, Bethany, for the introduction. Let me just share my slides. Hopefully you can see that. Excellent. As Bethany said in the introduction, I'm Mark Manning, founder and CEO of iTRACE Technologies. We're going to cover securing the aerospace and defense supply chains with non-clonable security markers. This presentation is based on a case study that was written by Rolls-Royce Aerospace. So iTRACE Technologies was founded in January 2016 in Silicon Valley, California. We've been delivering brand protection and supply chain integrity solutions for a number of years, specifically in the fashion accessory industries, medical device, aerospace, consumer electronics, and automotive verticals. I've been in the brand protection space and supply chain security since 2004. So I've been doing this for a long time. I've seen a lot of different technologies and worked on many, many different applications in the last 20 years. So we've actually won 2 of the case study contests. In 2022, we won the blockchain category with our parts provenance in aerospace case study. This year, we won the AIDC category with our secure product authentication. The case study featured Rolls-Royce Aerospace and their efforts to secure the aerospace and defense supply chains. So after rigorous testing from the cybersecurity team, the iTRACE 2DMI, two-dimensional marking identifier, proved highly effective with authentication tests, consistently identifying genuine parts and rejecting clones and copies. So what we're going to do is cover the case study that quote came from and review the testing that was done by the team at Rolls-Royce Aerospace as they went through their evaluation of the solution. It was tested by the Rolls-Royce cybersecurity team. They were mandated with securing the supply chain. So let's jump into the review of the case study. So Rolls-Royce had heightened concerns for the integrity of the aerospace and defense supply chain. Obviously, safety, quality, and reliability are shared priorities across all of the manufacturers of gas turbine engines. Rolls-Royce was seeing an increased risk from malicious nation-state actors that were trying to infiltrate the US defense and aerospace supply chains. Obviously, some of those countries have lots of resources and extreme motivation for infiltrating the defense and aerospace supply chain with substandard or counterfeit parts. And the supply chain is becoming increasingly complex, with parts coming from many, many different vendors and many different suppliers being built up into these systems. And as we all know, counterfeit parts cause significant damage. They can cause and have caused aircraft to fall out of the sky and other issues or accidents. The traditional paper-based systems and relationships can no longer be trusted. With the motivation of some of the nation-state actors out there, you can see that infiltrating a supply chain is a very, very good way of causing harm to an adversary. And I think we've seen that in the recent weeks with some of the attacks in Lebanon with pagers and walkie-talkies. If you can infiltrate the supply chain, you can do significant damage to the owners of that supply chain. And parts need to be authenticated throughout their life cycle. It's no point in just sticking a label on a package opening the bag, throwing the package away, and then expecting that part to remain authenticated for the rest of its life. So being able to authenticate and secure parts throughout their life cycle is extremely important on parts that have extremely long life cycles. Take gas turbine engines. They are an extremely harsh environment for track and trace technologies. They have high temperatures, extreme vibration, they're manufactured from specialist materials. There's stringent regulatory requirements that define how you use, manufacture, and maintain these parts. Aircraft engines require multiple repair and refurbishment cycles over many, many years. I understand that the average aircraft part can be in service from between 15 or 20 years and gets installed on multiple different aircraft throughout that life cycle. Having an authentication technology that can survive that environment and survive that life cycle of the parts means it needs to be robust, durable, extremely damage resistant, and able to authenticate that part with its data for a long period of time. So Rolls-Royce had some general requirements for an anti-counterfeit, an anti-clone solution for their business. So the requirements that they had meant that the technology needed to be supplementary to the traditional part markings that they put on those parts. There's a lot of part markings that are mandated and required by the FAA and various other regulatory bodies that are required and mandated for those parts. So this needed to be supplementary to that. It needed to have the option to be very small and covert, and we're going to cover the covert side of this in a few slides' time. But being covert and being able to be applied to very small parts was something that they were extremely interested in. It had to have low cost and low impact to implement and be implemented in an existing manufacturing infrastructure, which meant you couldn't forklift out everything that was already in place in manufacturing and put in some new fancy process that replaced what was already there. It needed to supplement and work alongside what was already in place. It needed to securely encode data separate from the traditional marking information. So be a solution that ran alongside the traditional marking and was encoded and secure separately for that. Provide minimal disruption and minimal added cost to apply, register, and authenticate. You can't be applying additional labels or equipment or other features to these parts. That was going to cost a lot of additional money. It needs to be durable and capable of surviving throughout the product lifecycle. As these parts go through the harsh environment, go through the lifecycle of repair and maintenance, the markings on them are susceptible to damage and wear and tear. So being able to survive that process was very important. It needs to be able to be read and authenticated using commercially available low-cost devices. And the best option for that is a smartphone. Everybody has a smartphone these days. Everybody understands how to download a smartphone app. It didn't require or shouldn't require specialist readers, forensic analysis, and other tools that would be necessary to authenticate a product. It needed to be authenticated by any user in the field at any time. Obviously, it needed to be very difficult to clone or counterfeit. Having parts that are authenticated is important, but it's pointless if the technology that's authenticating them is easily copied or cloned. And we're going to talk about that again in a moment with things like QR codes. And it needed to be compatible with being applied to microelectronics as well, without being damaged or causing damage or degradation to those microelectronics. So a very flexible solution that ran across multiple different kinds of products and different kinds of component capabilities. So what's been tried already in this space? So everyone's familiar with RFID and NFC chips these days. These are too fragile, expensive, and cumbersome for environments like a gas turbine engine. They just don't survive the life cycles of a turbine blade. They're great technologies for logistics. They're great for tracking packages and boxes, but they really are not suitable for harsh environments like gas turbine engines. They're generally not covert either. You can light up an RFID chip and NFC chip and find out where they are with very little effort. Nanoparticles and other additives that I like to call pixie dust, sprinkling things onto components in blobs of resin. Again, expensive readers or analysis, requires forensic analysis of the parts. They're very high cost in volume, too fragile. The epoxy resin components fall off of the blades of gas turbine engines and other components in those harsh environments. The long timelines to implement those programs means they're just not practical, and they're really not good at doing a unique identification application. You generally apply those on a lot or batch. It's very difficult to apply them in a UID application. And then we get to the QR code, barcode, and data matrix codes. These standard-based technologies are great. Anyone can apply them. Anyone can read them, including the counterfeiters and anybody else who wants to infiltrate the supply chain. Anybody can scan information off a QR code, create a new QR code, and apply that to lots of different products. They don't even need to copy the existing QR codes that are already there. These technologies are easily damaged beyond reading capability, easily counterfeit, and generally not covert in those kind of applications. By contrast, iTRACE 2DMI was highly damage resistant, is low or no cost to apply using existing infrastructure, uses mobile device applications for reading, and every single one of these markers that's applied to a unique object provides a unique identifier with provenance. It easily scales for any size of item, and we're going to see that in a moment on some images. And it supports the most difficult reading environments, low contrast, dark markers on dark backgrounds. And we have a secure artificial intelligence-enabled non-clonable and anti-copy detection engine that uses AI to analyze the markers and detect copies and clones. So everybody asked me, well, why can't I just use a QR code for this? Yeah, you've got this cool technology, but QR codes are everywhere and everybody is using QR codes. For many of the reasons that we talked about earlier, as far as nation-state actors infiltrating the supply chain and the scams and frauds that are occurring when people scan QR codes these days, the FBI, the Federal Trade Commission, US Army, Mobile Iron, even Witch Magazine, and many, many others have said, don't scan QR codes. Under any circumstances, QR codes are now a danger to your data and integrity of your devices and systems. And the alternative they gave was don't scan QR codes. So coming up with a technology or solution that's able to provide security on parts and components is becoming very, very important in the days where QR codes are no longer seen as a secure technology and are being used as ways of scamming people out of their money, personal information, and even gaining access to systems. There was a US power company that was taken offline when all of their systems were encrypted because one employee scanned one malicious QR code, and that took that power company offline. So it's not a concept that these attacks are occurring with QR codes. It's what's happening in reality today. So iTRACE 2DMI providing a flexible solution that can be printed on labels. It can be laser etched directly on parts, and you see on the left-hand side here, that's a beer keg with a marker being applied to it. And it can be dot peened onto different components. Now, that's an important point because some critical aircraft parts can't be laser etched. The heating process of a laser marking causes microfractures, which is deemed to make the part weaker, whereas dot peening has proved not to weaken those parts. Now, iTRACE 2DMI marks can be applied with printers, as you see on the labels on the right-hand side, with dot peen machines, as you're seeing in the middle, and laser marked using standard off-the-shelf laser technologies, as you see on the left. So being able to be flexibly applied to lots of different substrates, surfaces, components, materials in many, many different applications is something that the technology lends itself to very, very well. Now, we talked about difficult reading environments, low contrast reading on electronic components. So being able to put a dark marker on a dark background and still be able to read that marker and authenticate it with a mobile app. This is something that you can't do with a QR code, data matrix, or barcode. They require more contrast. They require big separation between the dark portions of the barcode and the light portions of the barcode. So being able to provide low contrast marking applications and secure microelectronic components alongside gas turbine engine parts, automotive parts, industrial electronics, and those kind of things, again, lends itself to a very, very flexible solution. When we talk about being covert and marking these things at a very small size, what you see on the middle of this slide is a picture of our marker on the hip of a diamond. That marker is about the width of a human hair, and there's a scale representation of a human hair next to the size of that marker on the diamond. So being able to apply these things extremely covertly on small components, small microelectronics, diamonds, or other things, again, adds to the scale and flexibility of this kind of solution, and was part of the reason why Rolls-Royce was looking at iTRACE to be able to provide a solution that covered any parts or components they were interested in securing. Now, this is the key to the longevity of an application in aerospace, being able to survive a significant amount of damage in a harsh environment. What you see in the photographs of these slides is markers that were applied, and these markers were applied to watches that were manufactured in China, in a factory in China. The factory production was being secured by iTRACE technologies, and the markers were shipped into distribution. We think the factory tipped off the distributors as to where the markers were because they were extremely covert, less than 0.5 millimeter wide. And the diverters unpacked the watches from their packaging. And this is in the thousands, not just one or two, but in the thousands. Unpacked the watches from their packaging, used sharp objects or engraving tools to try and scratch off or remove the markers from the backs of the watches. They repackaged them and shipped them back into Amazon, eBay, or Alibaba, the unauthorized marketplaces, at a heavy discount. When the brand discovered these watches for sale, they did sample purchases and then looked to inspect the iTRACE markers on those watches and noticed that someone had tried to scratch them, rub them, damage them to prevent the identity of the distributor being known. iTRACE was able to recover the information out of these extremely damaged markers, and you see the recovered line drawings of those markers next to each photograph, and provide the brand with the identity, the UID of each individual marker on each of those watches, which then was tracked back to the diverter or the last owner of those parts in the supply chain. So having a technology that can survive massive amounts of damage, even deliberate attacks from diverters, to be able to identify the source of those products was very, very important in the aerospace industry. Having a way to recover information from a marker that may have been damaged due to accident, wear, tear, maintenance, and identify that particular component and its data is very, very important on parts that have long life cycles. And we're talking electronics, aircraft parts, automotive parts, medical devices, and medical instruments. So then we get into the copies and clones, and we like to differentiate between clones and copies because it's an important point to understand the different attacks that can occur in a supply chain and identify those different attacks from a straightforward counterfeiter making a fake handbag or a fake pair of shoes. So clones versus copies. We identify clones as a reproduction of an iTRACE 2DMI mark from the original source file through repeated printing or repeated laser marking. Now, this is a very difficult attack to do, but not impossible for someone with a lot of resources or insider access to a manufacturing system. The iTRACE technology systems are put together and implemented to prevent these kind of attacks. Creating clones of a marker is only possible if you have the original source file, and that original source file only lives in the memory of the original printer or the original laser system. So it's extremely difficult to get. But if you have access to it, you can create clones of items, which are items manufactured on the same machine, using the same materials in the same factory as the original product. And applying an iTRACE marker to that product is the only way you're going to authenticate that. So for all intents and purposes, clones are the original products from the original factory with the original materials, but they're likely being sold out the back door of the factory, and the brands we're working with are not seeing any revenue for them. Very difficult to detect, impossible to prevent with QR code, data matrix, and barcodes. You just don't have the control or the security of those technologies to prevent it. Copies, on the other hand, are much easier to identify. People generally purchase a product or get hold of a product and reproduce the security markers on those products by copying them, photocopying them, scanning and reprinting them. With iTRACE 2DMI, they would only be able to reproduce the same individual marker. They would not be able to produce the next one in range, which means that they would have to create a whole number of products that looked exactly the same. And obviously with geolocation of mobile apps and database infrastructure that we have today, you could identify multiple authentications from different locations. And the counterfeiters will require the brand's own mobile app and key to be able to test their copies and clones if they were using iTRACE 2DMI. So an important distinction between clones and copies. iTRACE is able to detect both clones and copies of our markers. And this is an example of a printed authentic marker and a printed not authentic version, a clone of that existing printed marker. Now, these two prints were manufactured on the same print machine at the same time, using the same substrate, same ink, same materials. But our app is able to identify the registered authentic label that we produce first from the 100 subsequent clones that were created. And you can see that in the authentication score. And right at the bottom of the mobile app is the AI authentication score. And the AI authentication score goes from it actually goes from -1 up to +1. So 0.994 is the percentage score to say this item is the authentic, it's the original. It's very, very close to 1, which we deem authentic. The one on the right-hand side is a not authentic clone, a label that was made on the same machine at the same time, same materials, same inks. And that is scoring a 0.039, massive difference in the scoring between those two markers. So being able to identify clones of a marker on the same print system is what this app is able to do using our AI technology. We can do the same thing on aluminum parts. This is exactly the same application, but instead of being a printed label, it's an aluminum part where we created new markers that were laser etched at the same time on the same laser machine using the same substrate and the same digital source marker. Again, you can see the AI authentication score on the left, 0.994. That one's authentic. And on the right, 0.039. Again, not authentic. And this was with markers that were 6 millimeters and 8 millimeters square on these components. So being able to differentiate between clones and copies. Copies are so much easier to identify than clones, but our technology is able to do both. So what did Rolls-Royce do in their testing? What was their test plan and methodology? They wanted to create and authenticate very small marks on different materials. And that included aluminum and included some electronic components. They wanted to create markers using different production systems. They wanted to create markers using laser systems and dot peen. And they wanted to be able to detect clones and counterfeit of the markers and create the markers using industry standard laser engraving and dot peen equipment, the equipment they already had in their production facilities. So the team decided they were going to test clones as opposed to copies because they felt that would increase the demands of the capabilities on the iTRACE app and make it more difficult to identify. So they created one genuine item and 16 clones of that same item made on the same machine with the same material. The intent was to replicate a real-world attempt at producing cloned markers while they adjusted some of the parameters to determine which factors led to authentication success or failure. So they just tried to create some slight variation in the markers artificially on those laser systems, assuming that that would also happen in the real world. So the test results. All 16 clones were correctly categorized as not authentic, with a mean validation score of 12 and the highest one scoring a 13. And between each of the scans of the clones, each of the cycles of scanning the clones, the Rolls-Royce team scanned the registered genuine marker to validate that that marker also tested as authentic when it was scanned. And those scans scored 18, 18, 16, 18, and 17. So the lowest score was a 16. So the system correctly categorized the clones as not authentic and the original item as authentic. And the results showed that the iTRACE marks can be created by a variety of the technologies in the Rolls-Royce production environment, including laser systems, dot peen engraving, and we even showed them some print applications, allowing these marks to be applied to all items in the Rolls-Royce supply chain, including electronic components and the labels on their packaging. So that proved that iTRACE 2DMI is highly secure. Counterfeiters cannot reconstruct a 2DMI mark from scanned data or a copy. They cannot create the next 2DMI mark in sequence or range, and they cannot test the copy of a marker without having the brand's own app key and potentially the app that provides geolocation of every individual scan. So the counterfeiters creating copies would actually be giving away their location by testing to see if their copies actually worked. And it's also impossible to replicate all the parameters that the AI system is looking at when it's comparing the original component to the copies and clones. So the iTRACE 2DMI marking technology can be easily integrated into the Rolls-Royce existing production and operating plans and workflow. So how hard is this to do? So in another aerospace application, we went from a whiteboard discussion to production unit authentication in 6 weeks. And that included a 3-week approvals process for the specification and drawing updates. And that was a blockchain application that was registering parts on a blockchain. So not some antiquated database implementation, but new and modern equipment. But being able to apply these markers using off-the-shelf equipment in production environments, and even being able to have these markers from off-the-shelf security labels through folks like CCL Design Authentication. Having a mobile app authentication component for genuine parts on the label and packaging that matches the authentication components on the physical product itself. When the packaging is gone, the labels are gone, the product itself can still be authenticated even throughout its life cycle. So the Rolls-Royce product cybersecurity team found that the iTRACE 2DMI marks were secure, not easily copied or cloned, can be applied with a wide range of manufacturing technologies, including print, laser etch, and dot peen, authenticated with standard mobile devices, are highly damage resistant, and integrated easily with the existing Rolls-Royce systems and services. So that's the end of the overview on the iTRACE application. We're going to take some time now for some questions and comments, and I'll let Bethany work with you on the questions as they come up.
All right, here. So we have our first question. And what about UHF RFID tags using encryption or DigSig tags? Are these tags covert?
Generally not. Anything that's RFID is going to light itself up to let you know it's there when you bring an RFID reader close to it. So it's not necessarily going to provide a covert application.
All right, and then our next question here is your solution applicable in other vertical markets? Would only high-end / high-price products see the benefit of your solution? And can low-cost products see a cost benefit to your solution?
Yeah, great question. So we've worked with fast-moving consumer goods companies. The way our application is implemented is using a software licensing model. So with a software licensing model, there's generally no cost per part component to this. The software license is applied on a quarterly or annual basis, which means you can mark as many parts as you want to get the security level of the products you need. So as you scale the solution, the more products you mark and secure with this, the more cost-effective the overall application becomes. And our application scales based upon the value of the products we're protecting. So low margin, high volume products would have a lower license fee than high margin, low volume products. So think of it as the comparison between a Toyota car insurance and a Ferrari car insurance. You've got a lower value cost for your car. The cost for the solution would be lower. If you're doing high value, very expensive, lower volume parts, then this cost for the solution would be slightly higher. But we can scale this, the software license and the application to meet the demands of both high volume, low margin products, as well as lower volume, much higher margin products.
All right, and then another question we have here is, does your AI authenticator comply with ISO standards?
So the AI authenticator in our application is proprietary, as well as the security solution that we're providing, which is why Rolls-Royce wanted this to run alongside the other technologies that are implemented on their products. Being a proprietary security solution with our own embedded artificial neural network means that we have total control over the security and deployment of the application. We're not hindered or bound by the standards when supplying a security layer alongside or as well as the existing ISO standard applications. So we're a security layer, a security component that does not interfere or change the ISO standard implementations that are required or used on the existing parts. Think of it as a security layer that augments or enhances those ISO standard solutions that don't necessarily have security embedded into them. The Digital Product Passport, for example, the Drug Supply Chain Security Act, those technologies are generally using barcode, data matrix, or QR code, open source, and the security is only at the database level, which doesn't necessarily secure the component. So we are an augmentation to the ISO standard implementations.
All right, and then we have another question here. Can you please explain how a counterfeiter would give away their GPS/location if your systems is utilizing 2D/QR codes? How can those technologies send a signal to give away their location?
Yeah, our solution is not using QR codes and standard 2D codes. Our solution is using the iTRACE proprietary 2DMI markers, which require the iTRACE app or the integration of the iTRACE app into the systems to be able to read those markers. Part of that app's capability is a geolocation of every scan that is used by that app software. So counterfeiters can't just take a standard camera and use our code like a standard QR code. We don't use QR codes in our implementation. We use our proprietary markers, which require our software to be able to read them.
All right. I think that's the end of our Q&A session. So if you could go to the next slide, Mark.
There we go.
If you want to reach out to us here at AIM, our information's on the screen. If you want to ask more questions to Mark, his information is on the screen as well.
Excellent. Yes, and you can download the case study from the AIM website. It's available to everybody that's has access to that AIM site. And the case study actually has a lot more detail than we had time to go through on this presentation. So I look forward to any questions, comments, feedback that the people have from this slide presentation and the case study itself.
All right. Thank you, everyone, for joining us today.
Thank you.